Okay, so in this video we want to show a reversal. So we said in the last video that compactness for sentential logic and compactness for the 0, 1, the intervals in the reals, the topological compactness are very closely related, and we showed how compactness for sentential logic implies compactness for the topological compactness on 0, 1. So what we want to do here is the reversal. We want to give a new proof of compactness for sentential logic using the topological compactness. Okay, so this is a new proof of compactness, very different than the one we did originally, but now we're going to use the fact that the interval 0, 1 is compact. Actually, we're going to use the fact that the Cantor set is compact, which is also equivalent. Okay, so that's what we want. The proof of compactness for sentential logic using compactness for Cantor set. Let's start by looking at Cantor set. You guys have, I'm sure, seen this guy before. This is what is called the 1/3, 2/3 Cantor set. So you start with this interval 0, 1. And you're going to remove from it the middle interval 1/3, 2/3. Okay, we're going to remove that one. And we are going to be left with two closed intervals from 0 to 1/3 and from 2/3 to 1. And now we're going to remove the middle third interval. We're going to remove that one, we're going to remove that one, and we're going to end up with now 4 intervals which go from 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, 8/9 to 1. And we keep on going like that. And we keep on removing the middle intervals. And we end up with that, and then we remove the middle intervals again. And we keep on going like that, and at the end we're going to end up with what is called the Cantor set at the end. So we keep on going in that direction, removing and removing and removing and removing, and that's how we get the Cantor set. The definition I wrote here is different. It's a set of all the numbers you can write in this form, where for these a sub n's are a sequence of zeros and twos. So why is that the case? Well, let's see. Suppose you have a number, I don't know, let's say somewhere here. Okay? So here is their number. Well, actually, it has to go down and at the end, right? So how do we write that number? Well, let's see. So the number belongs to this interval right here. So that means it's more than 2/3. So that is 2 times 1/3. This is this number up here. Plus, well, it stays on the left side then. So we don't know how to add anything. But now here it goes to the right side. Right, so it comes up here. What are we adding to come up here? We have to add 1/27 because this interval up here is 2 times 1/27, so this is 2 . One over 3 to the 3, and then that is going to leave us at this point right here. We're at this point right there, and now we want to go up here, so we have to add again plus 2 plus 1 times 1 to the 3 to the 4, and that leaves us up here. Okay, so essentially what we're doing is if we want to stay in this interval, we don't add a third, and if we want to stay in this interval, we add 2 plus 1/3. Then we want to stay, if we are here and we want to stay on the left, we don't add anything. If we want to stay here, we need to add 2 plus 1/9. And if we were here and we want to come up here, we need to add 2 plus 1/9. And then the same on the other ones. Whenever we are in an interval and we want to go to the right hand side, we have to add 2 times, well, 1/3 to the 3, here is 1/3 to the 4, 1/3 to the 5, right? So every number that you can write as a series like these are exactly the numbers that you get in the Cantor set. Okay, so this is another way of saying this is these are exactly the numbers that if you write on base 3, in base 3, then all the digits you use are 0 and 2. And so you can write these numbers in base 3 without using the number 1. And that's exactly the middle third Cantor set. Okay, so that's the Cantor set. How are we going to use this? Well, a corollary of the compactness of 0, 1 is that the same thing is true about the Cantor set. If you have a bunch of a whole set of open intervals with rational endpoints which cover the Cantor set, the C, they are covering everything, then there has to be a finite number such that those intervals are enough. So every infinite covering of Cantor set by open intervals has a finite subcovering. You didn't need all of them, finitely many were enough. Okay, so that's what it says. The reason this follows from Cantor's from compactness for 0, 1 is because Cantor set is to build Cantor set. What we're doing is removing countably many intervals like this 1, 2, 3, 4, 5, 6, 7, 8, 9, and we keep on deleting open intervals of rationals. So if you add those intervals to this list, the ones that build the Cantor, the ones that you remove in the Cantor set, then you're going to get a covering of the interval 0, 1, the full interval 0, 1, right? So if you add those intervals here, you cover the whole interval 0, 1, and then you can apply compactness for 0, 1 to deduce that there's a finite subcovering. And then you get that finitely many of these guys are covering the Cantor set. Okay, so I let you guys work that out. Do it, because it's a nice exercise in topology. Okay, so we're going to use this one directly. So we're going to use the compactness of Cantor sets to prove the compactness of sentential logic. So what is the connection? How are we going to connect Cantor set and sentential logic? And the connection comes from this map. So this map, we're going to define the map C. And C, what it's going to do is going to take a truth assignment, V, and it's going to assign to V an element of Cantor set. So V is a truth assignment. It's a map essentially from the set A1, A2, all the way for all the n's into true and false. And for each such assignment, we're going to assign a point inside Cantor set. And it's going to be a bijection actually. Each point is going to correspond to an assignment and each assignment to a point. And that's the way you do it. The way you do it, the formula is right there, is you sum all these elements 2 times 3 to the minus n, where for all the n's where you get true. Okay, so if an is true, you add this one. If an is false, you don't add it. Okay, so essentially, suppose you are given an assignment V, and what you do is the following. And you want to choose a point here in Cantor set. So your assignment V, so you look at the assignment V and you say, okay, so A1 is assigned true or false. If it's assigned true, go to the right. If it's assigned false, go to the left. Okay, now A2, is it assigned true or false? If it's true, go to the right. If it's false, go to the left. Now, variable A3, is that one assigned true or false? And then again, true means move to the right, false means move to the left. So each one corresponds to a variable. So this one corresponds to the variable A1, and this one A2, and this one A3, this one A4, this one A5, A6, all the way. And your variable assignment is assigning a true or false to each of these variables. So you look at true is to the right, false is to the left. So essentially a whole assignment of true and false is essentially the same as a whole assignment of left and right, and we are going to end up with a unique point. And the same the other way around. Whenever you have a point, the point comes from some path, some way to reach the point, going left and right, left and right, left and right, and that's going to give you an assignment for the variables, right? So essentially the space of all truth assignments looks exactly like Cantor space. But and so for instance, like, as you guys know already, when you have like 3 variables, essentially you have 8 possibilities, 1, 2, 3, 4, 5, 6, 7, and 8, and those are the 8 coming truth assignments with 3 variables. And then when you add one more, you start having like 8, and then, well, 16 and more, and like that's what Cantor set is being. Each interval is being divided in 2, in 2, in 2, in 2, given weight for the possible combinations for the truth assignment with more variables. Okay, so now we have our map that assigns true assignment. Each true assignment gets assigned a point in Cantor space and vice versa. Okay, so here is just a copy of what we know so far. The definition of Cantor sets is all the points of these forms where a sub n is either 0 or 2. So they are these things you can write that way for all the sequences that you have. And we have a map that assigns to each variable truth assignment v a point in Cantor set. It just looks at all the places where you get true, and for those n's, you add the term 2 to the 2 times 3 to the negative n. Cool. Okay. And now what we want to do is to show, this is the main observation, that for each sentential formula phi, well-formed formula phi, there exists a set of rationals, a finite tuple of rationals, such that the formula is going to be, so given evaluation v, the formula is going to be assigned false if and only if the point that corresponds to that valuation belongs to that interval. Okay, makes sense? Let's look at this. Let's first look at an example. So there we have a little picture of a Cantor set. And suppose you have a formula phi. So let's consider the formula phi being a1 implies not a2 or a3. Okay, so this formula only uses a1, a2, and a3. So we only need to worry about the first 3 levels of the Cantor set. But the Cantor set contains, keeps on going, and at the end we get a limit. I only drew the first 3 because those are the ones that show up in this one. So let's see what the truth table is for this guy. So this one is only true in the case when you have true, false, false. So true, false, false is going to correspond to true means go to the right, remember, and false means go to the left. So you go to the right once and then to the left twice. So you're not going to end up with this guy up there. That's the only one that corresponds to true. And then everybody in the Cantor set that is included in that interval, those are all going to give you true, and all the other ones are giving you false. So you need intervals. You need these intervals that cover the rest, right? So we need an interval that covers this part and an interval that covers this part, and leaves out this part of Cantor set. It's left out. This one is not covered by the intervals because that's when you get true, and in the intervals that's when you get false. Okay, so then those are the intervals we're going to choose, whatever those intervals are, which is a bit hard to calculate. 15 18s, we can use here -1, we can use here 1/2, and we can use here, let's say, 2. Those intervals are going to cover all the falses and are going to leave out this little interval that is true. We may have more intervals that are true and more that are false, so we can always use enough intervals to cover the parts that are false and not the parts that are true. If you have more variables than just 3, Well, we will have to look further out. In Cantor set, we have to look down, use more variables, but it's always finitely many. Each formula only uses finitely many variables, so we only have to look finitely far in this construction of the Cantor set. And some of the intervals are going to correspond to true, some to false, so we can always find these open intervals that cover the parts that are false. Okay, and that's how we get the observation that for each sentential formula phi, we have these finitely many intervals that cover the false part. So how are we going to use that? Well, now given a set of well-formed formulas, gamma, consider all Ri's and Li's corresponding to all formulas in gamma, right? So put all of these together. For each one we have finitely many. Put all of them together. Now we have a lot of intervals. We have infinitely many intervals. And then what do we know? So now we know for evaluation V, we know that V makes gamma true if and only if the image of V, the point in Cantor set that corresponds to V, does not belong to the union of all these intervals Ri, Li. Now putting not together all the formulas that belong to gamma, right? Put all the formulas together, and then you have to be outside. To be true, you have to be to make all the formulas true. So that means to be true, you have to be outside all these intervals, right? So false means inside. So to be true, you have to be outside these intervals, and you have to be outside all of them, right? So in other words, so that means for evaluation, to make all the formulas true, you need to be outside all the intervals. So we can rewrite these as gamma is satisfiable. Satisfiable means what? Satisfiable means there exists evaluation that makes it true, right? So that means there exists evaluation whose point in Cantor set is not in those intervals, right? If Cantor set is not covered by these guys, that's exactly what it means to be satisfiable. It means there exists evaluation, so that means there exists a point that belongs to here and doesn't belong to here, right? There exists evaluation that makes it true. That means there exists evaluation that doesn't belong to these guys, but belongs to Cantor set because that's where we assign the evaluations. So satisfiable means that it's not covered, right? And so now compactness tells us, well, by Cantor set we know that if this is, so then we get that saying that all finite gamma 0 including gamma are satisfiable. It's equivalent. Well, you have to look at the intervals that correspond to the formulas in gamma 0, right? For each gamma 0 we have finitely many formulas. So saying that for all the finite ones are satisfiable, that's the same thing as saying that for all number k, the union of all the i's less than k of the interval Ri, Li is not a covering, right? So whenever you choose finitely many formulas, if you look at what only the intervals that correspond to those formulas, they don't cover everything. So there exists something that makes it true. And now if you look at what compactness is saying exactly this. That if for all finite ones you're not covering, then the infinite ones is not a covering, right? It says the contrapositive. If the infinite one is a covering, then some finite one is a covering. So that's the same thing as if all finite ones they are not covering, then the big one is not a covering, right? So that's what compactness theorem says. So therefore, we go around and we get that if all finite subsets of gamma are satisfiable, then gamma is satisfiable. Right? Via this is compactness for the Cantor set. So, right, so we get from that implication on the right side, compactness for Cantor set, we get compactness for sentential logic. And that's how we close the circle. Compactness for the topological compactness is equivalent to sentential compactness. And then we can apply a lot of corollaries that follow from sentential compactness. See you guys next week.